University of Cambridge, and today my talk is Don't Interrupt Me While I Type, Inferring Text Entered Through Gesture Typing on Android Keyboards. So essentially this talk is about the study of a new side channel that we have explored on the Android operating system. More specifically in this talk we exploit the so-called procfs virtual file system, which is mounted by the Linux kernel at boot time under /proc. And this procfs file system is called virtual simply because the files that it contains do not correspond to data stored on disk. Instead, the information you find on in those files are various pieces of information which are typically used for troubleshooting purposes. So under procfs, we find application-specific virtual files that contain information about applications and processes. So for example, there's a file called tcp-send, which basically contains the number of bytes that every particular app has sent over the network. So not surprisingly, those application-specific virtual files have been shown repeatedly to enable substantial side channels. And so in the latest Android version, those files have been locked down and they are no longer readable by third-party apps. However, under procfs, we also find global virtual files that contain information about the global state of the system. And those global virtual files are still accessible even in the latest Android version. So not surprisingly, these are the files that we exploit in this work. To be more specific, there are two pieces of information that we leverage. The first is the number of hardware interrupts that the Android kernel receives. And the second is the total number of context switches that the OS undergoes during user input. So to make sure we're all on the same page, I'll assume for the rest of this talk that the user has installed an app which is Curious on his phone. And this Curious app is trying nevertheless to infer what users type in other apps on the phone. And this Curious app doesn't require any permission whatsoever. I'll further assume that the user makes use of the so-called gesture typing feature that most modern smartphone keyboards have. So with gesture typing, you can essentially enter words in a keyboard by dragging your finger from letters to letters. So there's an example here with the word hello. So what would happen is the user would put his finger on the letter H, drag it to E, then L, then O, at which point he would take his finger off the phone, of the screen. So something I want to point out here is that if you look at letters in the word hello, so for example the letter E, what you can see is that every time the finger hits a letter, it's changing directions. And this effectively requires the finger to slow down right before it reaches E, at which point it has a speed which is virtually null, and then the finger will accelerate again in the other direction. So I'll just get back to this later on in the presentation. So there are two things that make the attack possible. The first is that every time you move your finger on the screen screen reports the finger position update to the Android kernel, and this is done through the generation of hardware interrupts. And so you can see that the number of hardware interrupts that are received does in fact leak some amount of information about what users have typed. Second, the application, so the genuine keyboard app, where you enter your text, also needs to retrieve the position update of the finger from the kernel. The keyboard app runs as a standard process on the device, and therefore, to query the kernel, it has to do some context switches. And essentially, again, the number of context switches does reveal some amount of information about what users have typed. And so in this work, we leverage both the hardware interrupts and the software interrupts to our advantage. So this graph shows you the speed at which the total number of context switches varies when a user types the word hello as a function of time. So the blue line is the actual data recorded, and the green line, the dashed line, is the average data. So what you see is that when the finger starts at the letter H, the speed of the total number of context switches increases, then it remains constant for a little while, and then it decreases. Okay, and the pattern repeats itself for other letters. So in fact, the speed of the total number of context switches loosely reflects what the finger does on the screen. As I pointed out earlier, the finger accelerates, remain constant, its speed remains constant for a little while, and then the finger slows down. And the reason why it slows down is simple, is because as I pointed out earlier, the finger is going to change directions, and therefore there's a decrease in speed here. So we're going to use the speed of the total number of context switches as one of the features to train the classifier later on. So here at the top, you see the total number of hardware interrupts that the Android kernel receives when a user types the word hello again. In between letters, you see that the number of hardware interrupts received grows linearly as a function of time. And then for each letter, you see those little plateaus. And those plateaus, in fact, correspond to the time when the finger has a speed which is virtually null, which I pointed out earlier. So when the finger has a null speed, essentially just means that it's not moving, and therefore the screen need not report any updates to the OS kernel. And therefore the total number of hardware interrupts received remains constant. Okay? So I'll refer to those plateaus as simply the zero speed events in the rest of this talk, because they correspond to the finger having virtually a null speed. So what we do in this work is we use the position of those zero speed events as one of the features to train our classifier. So what we would like to be able to do is be able to precisely locate where those zero speed events occur. And that's what's depicted in the second image. Unfortunately, in practice, everything doesn't work out as well as we would hope for. And what we only manage to get is what's depicted in the bottom picture. It's this kind of distribution of zero speed events. Okay? And there are two reasons why we can't precisely locate those zero speed events. The first is that users move their finger really fast on the screen, and that makes the signal really noisy. And the second is that for certain words, there simply aren't any zero speed events at all. For example, if you consider the word ask, A-S-K, the finger might just go straight from A to K without stopping at S. Okay? But more generally, users tend to move their finger on the screen not using those ideal straight lines that I showed you earlier. The trajectory of the finger looks more like this curved shape for this light blue color word here. And this makes the signal even noisier for us to be able to infer words. But nevertheless, the presence or the absence of those zero speed events, as well as their distribution, do in fact correlate to what users type on the screen. So another piece of the puzzle is, as I said earlier, we have this curious app on the phone which is reading those virtual files and extract the interrupt data. So the interrupt data appears to the app as a continuous stream of data. And to be able to extract features for each word, it first has to be able to figure out where the words are in this continuous stream of data. So to do this, we reuse the hardware interrupt counter. So this picture here shows you the interrupt counter for the sentence, I trust you. Here on the right, you notice the zero speed events I talked about earlier for the letter O of the word you. But something that's more striking in this picture is the zero speed events in between words. And those, in fact, correspond to the time when the finger is lifted off the screen by the user in between words. Okay? Because those zero speed events last much longer, we can use them to identify exactly where the words start and end in the stream of continuous data that we get. And this works reliably in practice virtually 100% of the time. So to summarize, in terms of features, we use the length of the words, the position of the zero speed events, the one for the letters, and the speed of the software interrupt counter, also known as the context switch. And then we feed this to a classifier. So in terms of classifier, so we've looked at traditional classifiers such as an SVM, which take as input a single vector of features corresponding to a word, and then predicts another word. So we looked at the SVM. It worked well for some users and quite poorly for other users. So we tried to look for other possible classifiers. And the thing that we wanted to be able to model is the fact that a word can't actually be predicted in isolation. A word belongs to a sentence, it belongs to a context, and so we wanted to be able to model the fact that a word depends on all the previous words that come before it in a sentence. So an HMM is one step in this direction, but it can only model the dependency between a word and its predecessor. So in fact, it turns out that we can do better than an HMM, and we can use so-called recurrent neural networks. These are neural networks which have been extensively studied by the NLP community. And those can, in fact, model the dependency of a word and all its predecessors. In practice, what that means is that instead of, like for an SVN, instead of giving as input a single vector, we're going to feed the RNN with a list of vectors where each vector corresponds to a word in a sentence. Okay? So I won't get into the detail here, but if you're interested, it's in the paper. So in terms of evaluation, we looked at the Google keyboard. We had a real chat corpus of 10,000 English sentences, which was collected by another group of researchers back in 2006. Within this corpus, we limited ourselves to the most common 200 words. The reason for this will become clear in a minute. For training, we had each of our participants enter a series of words in an application that we developed. Each word occurred roughly 20 times. And so in total, each participant entered roughly 4,000 words. It took each of our participants between a week and a month to complete the task. And so it was so time consuming for them that this explains why we limited ourselves to the most common 200 words during the study. So something that I didn't mention explicitly, but which is true for usually all kinds of classifiers, is that when during the prediction phase, the RNN, the recurrent neural network, doesn't just give us the word that it predicts. Instead, it gives us a list of the most likely words that the user has entered. Okay, so the word that appears in the first position is the most likely, the one in second position is the second most likely, and so on. So on this graph, what you see is the prediction accuracy for a single word prediction. The first bar here essentially tells us that roughly 34% of the time, the correct word entered by the user appears in first position in the list that the RNN has output. And then 10% of the time, the correct word appears in second position in the list, and so on and so forth. As part of our evaluation, we also looked at trying to re-identify users that post messages anonymously on messaging boards. So there's this app called Yik, which apparently is used quite a lot in the US, and it allows users to post messages anonymously on a messaging board. And by anonymous, it just means that there is no username or pseudonym associated with the post. And then other Yik users can read those messages so long as they are physically in the vicinity of the sender. Okay, but they can't tell who posted which message because of the lack of username and things like that. So what we try to do here is trying to re-identify which sentence was typed by which user. And I repeat myself, but we're still assuming that every user has this curious app installed on the device. Okay? So I can't go into the details on how we get from the RNN prediction all the way down to how we re-identify users, but I want to give you an overview of how well we can re-identify users in practice with the techniques that we described earlier. So this line here, the blue line at the bottom, corresponds to a set of 35 sentences. And the point right here in the middle corresponds to sentences of length 3. Okay? So for this scenario, we can roughly, we can re-identify users 80% of the time. Said otherwise, we can re-identify 80% of the users. As the number of sentences decreases, so as the number of sentences posted on the messaging board decreases, the predictions improve. And so for a set of 10 sentences, we can re-identify roughly 93% of users. And then as you move towards the right side of the graph, the size of the sentences grow bigger, and the predictions also improve. And this is kind of intuitive because the more words you have in a sentence, essentially the more data you have, the more information you get, and therefore the easier it gets to re-identify users. So to wrap up, so what we did in this work is we try to show that hardware and software interrupts do correlate to what users type on the device. And more importantly, that global virtual files do enable new side channels. We think we could improve the results if we had more data to train the RNN with. And in terms of future directions, it might be possible to reuse the hardware-software side channel to attack more traditional keyboards. And more generally, it might be also possible to try to infer what people do on their phone using this new side channel. And that's all. Thank you.